Here's what the final result is going to look like, and as one can see, there's a bunch of stuff going on here, like some fireworks display, these waves and clouds, with dynamic speed and alpha, and with the projectile motion. If there's only one of these, one can just put all the code in a single script. But this video is about what one can do, pretty generally in Python, when reaching the point when one needs to start thinking about how objects can be organized into code modules, classes with inheritance, data structures, etc. So software engineering aspects. But it's also going to get into some of the Matplotlib animation library and some NumPy and math, because that's what's producing this motion. You may be wondering, why do this in Python Matplotlib? Why not Unity or Unreal? And it's because the main topic in this video is object-oriented programming. Sure, you can learn that using Unity and Unreal. Also, other Python libraries could be used, like manim, pyopengl, pygame. Matplotlib is good if you're already used to Matplotlib, from making data plots, for example. That's what most people use it for. And then want to take it one step further to generate some relatively simple animation. Most people do their first animation in a single simple script, and this video is about taking that one step further. So this is just a visualization of 3 Python core classes, which are then the parents of one or more children classes. It's pretty common to see something like that in programming generally, where there is a timer, and the things that are happening at different times need to be controlled by some logic, which can be distributed among classes. Here's the project as it appears in the PyCharm IDE. It's also shared on GitHub exactly like this, so check the link in the description. I always try not to have more than 10 folders and files in this outer level. Everything else is nested away in folders except for 2 .py files. One is main.py, and this file is always there. Whenever I do something object-oriented, it tends to always be there. It can also be thought of as the controller in the MVC framework. The other file is called Big P, and that is the shorthand for parameters, or specifically it's the global parameters. In this case, it's what is the dimension of the map, how many frames are to be animated, what is to be animated, and how many of what should be animated. That's this num. The idea here is, if a parameter is global, that is, it's used here and there by various modules, just put them in a single file. Don't spread them out in different places. And then, in the code, just import the global parameters like this wherever they're needed. One important folder in this project is this folder named O0's info. And O0 stands for object 0, and the 0 gives the family rank of the object. So an object 0 is a root object which is highest up in a family tree, and then it has children which are named O1, and the O1 objects have children named O2, and this structure is generic for the whole program. And when a root object is initialized, it's done with one of these info files. So these 3 Python files are basically an extension of the parameters file for the projectiles, waves, and clouds that are being drawn in the animation. Waves, for example, is a class that contains all information about the waves that are shown here. In a previous project, this whole class would instead be a JSON file to describe like where a certain object is, how fast it should move, and how many frames it should use, etc. But I've transitioned more and more to just use a Python class instead of a JSON here, because then one can do all kinds of other stuff like assertions or have code that generates the contents in these Python dicts, which clearly look like JSON a lot in many places. So there's no real need to work with JSONs directly to represent the parameters that these objects use individually. On the notation, the _s thing here is my abbreviation for the Python self, and the GI stands for general info. So that's the general information regarding the children and grandchildren of the waves info class. And here in this module, an instance of this info class is generated and stored in a dict called GIS, general informations. The next folder is the pictures. It contains pictures that are also loaded into this object structure with the same convention as the general info. Here in the O0 folder, for example, I have an O1 folder, and this O1 corresponds to the O1 described in the info file. In this particular object structure, the O1 objects always get a PNG picture loaded into them. But for the waves, no PNG is being shown, so there it's just a placeholder. But for the clouds, there are 4 different types of cloud PNGs, and basically here each object gets its own PNG. On the other end, the children of O1 in this object structure, that is O2, are always rendered without the use of a PNG picture. The difference can be seen clearest here. So if an object is O1, an ImShow of a picture is used, and if it's O2, a plot of coordinates is used. So the projectiles, the fireworks after the explosion, are essentially a list of XY coordinates rendered as lines using plot. But they also have a picture of the rocket, which is rendered up here. But importantly, both the picture of the rocket and the following lines all belong to the same object. The waves have a placeholder picture up here, but what is actually being shown is just a bunch of dots with turquoise color and marker set to O and a pretty large marker size. The clouds are made up of pictures. They don't do any plot of dots, so it's just a pass down here. One could ask, why isn't this ImShow for the waves just a pass, like down here, instead of this placeholder picture? And it's definitely possible to do it that way. The simple explanation is that the O1 objects are higher up in the object structure in this particular program. It was just convenient to always require it to have a picture to make the code more generic. Concerning disposition, all the code except for main.py and the parameters file goes into the source folder, and that contains everything. So this module, which essentially renders the objects, and these modules for the O0, O1, and O2 objects, which computes their motion, like these XY arrays, and things like load pics, which basically is the operation of moving a PNG into a correct O1. I try not to have more than, say, 10 files at this level. If there are too many files in here, it's a sign that it's time to think about dividing up the code into subfolders, and which file should go into which folder. Related to that, if a code in a single Python file, aka module, grows too long, it usually means that it should be split up into separate modules. Usually for me, I start feeling the urge to do this when the code in a single module starts exceeding 200 to 300 lines. That's some kind of threshold where I can kind of keep all that code in my brain's short-term memory. When I scroll through code files with 600 to 700 lines of code, I tend to get lost. Distributing code among modules is not only a good thing, however, and one will find oneself trying to remember which module a certain code exists in, but that's better than scrolling through a single module with 700 lines. Same thing with functions. If there are too many functions in a module, that's a sign that a module is too large. Also more of a opinionated thing, but I'm not a big fan of nested functions like this. I like to be able to quickly collapse all the functions in the module so one can get a good overview. And nested functions just disappear, at least when using Ctrl-Shift-minus in PyCharm. It's supposed to be possible, but the shortcut keys that they say should work don't for me. I'm not going to go through all the code in here, but focus on what these modules mean and how they're used in main.py. After the imports, there is this write variable that says whether the animation should be written to file or animated live. If it's written to file, these two ffmpeg writer lines are used. And down here at the bottom, it's either plt.show or ani.save. That's part of Matplotlib animation basics, and I'm not going to go into detail on that. I put the link in the description to a previous video where this is covered. And here there's frames per second. Then there are two lists, the list of drawables that are being returned in the animation loop. One can use a single list here, but sometimes it can be nice to separate them, and in this case the axis 1 list just contains the black background pic, which looks like this, where the axis 0 contains the objects that are moving. They're added to axis 0 when they are being shown and removed when they're not shown. Then these 4 lines basically generates the contents of this object structure, and what comes out of that is this big O0, which is a dict that contains 3 roots, one for the projectiles, one for the waves, and one for the clouds. Also notation, whenever big O is used, it means that it contains multiple objects. And whenever a small o is used, it means that it's just a single object. Then there is this important comment here that says viewer, and that comes from the model viewer controller idea. Basically everything up here is pre-computed within milliseconds, and I usually put a breakpoint here. So if there's something that one wants to pre-compute quickly and debug, for example checking this object structure, that can be checked by just putting a breakpoint and having a look at the variables. Right, then comes the animation loop. This init function doesn't contain anything, it's just needed for bleeding to work, I think. Then it's usually a good idea to make it print something at each frame. So the I iterator is the frame, and then this is a list. So in this function, one can just append stuff to the list and print it at the end of each frame. So what's being looped over here? In the outer level, it loops over the O0 objects, that is the root objects of the projectiles, waves, and clouds. These O0 root objects are just containers. They don't show anything in this program. But then it starts looping over their children, the O1s, inside these nested loops. Just for clarification, every unique thing that is seen in the animation here is an object instance, but it's not compulsory to do it like this. Matplotlib doesn't need any class instances to work. It just needs a pointer to circle X object, which depends on whatever you want to show, like a picture or just some single pixel coordinates. And the call to this rendering function is done from inside here. So basically, there is an instance of this O1 object, for example, that contains this PNG picture and optionally XY coordinates, if those are needed. And all the code that is needed to describe the changes to this picture or the coordinates through time is living in this class. As one can see, there's some ugly if-else things here, like if projectile do this, if cloud do that. And alternatively, one could instead have written a projectile class and a cloud class. But in some way, there's no free lunch. There's always going to be some ugliness in defining a boundary between what is generic and what is not generic. Like in this program, the projectile cloud separation is made here on the parameter level. It's only simple stuff. And while theoretically one could have moved much more code into these classes, that has the risk of leading to a bunch of redundancy. And then one needs to add stuff like more interface modules or inheritance to get rid of that. And that can also become pretty ugly. One important thing that each of these object instances hold is information about when it is to be shown. So for example, each of these O1 objects have these init frames, which gives the frame that it is going to be drawn. And basically when the animation loop is running, it should only do work drawing this object whenever I here in the animation loop is the same as this init frame, and then continue drawing it until it reaches a stop frame later on. Like the computer should not have to do any work on this object whenever it isn't shown. For this to work in practice, a couple of more things are needed. Like each instance here needs to keep track of how many frames it has drawn. I call it a clock here. So this is an abstract class that is inherited by all the object instances. So they all have this internal clock that starts at 0 and starts being incremented after the first frame has hit the init frame. So this first loop checks when objects hit a certain frame, and if so, it runs some finishing code that doesn't take any time, most important of which is to say that this object is now supposed to start drawing, and sets the start and stop frame of the object. That's this set frame SS, SS for start stop. And then the second loop checks that if an object is drawn, it starts incrementing the clock, and if drawn is set to 1, an X object is created, added to axis 0, and then updated for a number of frames until it reaches a frame when it is removed from axis 0. There's lots of coding details that I don't cover here, and this whole upper loop could possibly be done before the animation loop. There's always some things that can be improved and there's some redundancy. The main message is that an object before or after it's to be shown in the animation should not be inside whatever is returned from the animation loop, because that is one of the biggest sinks when it comes to CPU time. So in summary, this loops over objects and prepares them when they hit their init frames, renders them and adds them to axis 0 at that same frame, then transforms them for a number of frames and removes them at a specified stopping frame. By the way, it's also possible to use a dict instead of a list of the X objects that are returned here, which is pretty convenient to remove objects. But I don't think bleeding works then, so lists are used here. And each object has an index to where it is in this list, and that way it can also be removed. It's pretty ugly, but it's worth it to get bleeding. Moving to the higher abstraction level. Abstraction / polymorphism / inheritance is one of those things in object-oriented programming taught in beginner level courses for a reason, so use it. Often in code courses, one gets dropped this big code that has a bunch of inheritance, and the creator of the code will say how important the inheritance is to make sense of everything, etc. And then one doesn't understand anything. One issue is that code, when written the first time, doesn't fit well with inheritance because it's hard to know what a good inheritance structure will end up looking like. And same goes with understanding it. It just takes a while to make sense of it, especially when it's written by someone else. Whenever one writes an abstract class from which other classes inherit, one essentially forces the users of the abstract class into a certain mold, and the problem is that even late in a project one may wish to change that mold. So in some ways, inheritance is not just preventing some degree of project flexibility, it's working directly against it. But it's also good. So one way to make sense of all this is through some pretty general metaphors. Like, which code is simpler to write and understand when we want to find a certain element in a data structure? Is it easier in a list or a tree? So a list is a metaphor for no inheritance, and a tree is inheritance. The list is a heap, and the tree is a hash map, say. Or lines versus triangles. Are lines better than triangles? Both of them have advantages and disadvantages. In this program, two abstract classes are used here, and they're used to construct these object instances. And the clock that I mentioned before is a good example of something that is suitable for inheritance. I'm not going to go into detail because the cat, dog, animal thing one gets taught in introductory programming is really all one needs to be taught about it. If there are 5 cats and 5 dogs that are doing the same thing the same way, one writes an animal class to avoid redundancy in code. I mentioned before that this first loop inside the animation loop runs some code about when these O1 objects and their children are to be shown, and that could technically be pre-computed up here before the animation loop. So why wasn't that done? The code up here's job is to pre-compute as much as possible so that the animation loop can be as fast as possible. But while that is true, it's also true that that is a utopian dream. So it's something to strive for, but it's also easy and tempting to put code into the animation loop, because why not? There is the counter and all the other objects are in there. So it's pretty easy to get an overview of everything that's going on in the animation loop, which is especially convenient when debugging. But as the project grows and rendering time increases, the code one puts in the animation loop tends to take longer and longer. Putting code before versus inside the animation loop is like a trade-off between either developing quickly early in the project or developing quickly later. Also, one thing to remember, wherever one chooses to put the code is where the bugs will happen. Say, in a larger project that the code before the animation loop takes 10 seconds to run, but running the animation loop with all the Matplotlib rendering may take minutes or even hours. So what if a stupid bug happens after 2 hours of rendering down here, just before the animation is complete? It's a disaster. 2 hours are lost. So generally it's good to put as much of the code as possible before the animation loop, because if one doesn't, one is going to lose time debugging bugs that occur after 2 hours, at least in larger projects. This particular animation takes about 10 minutes to render 25 seconds at 80 FPS. One important thing is to be able to easily switch between the number of objects that are being shown. So when building the animation, one can just start with a couple of objects or just working with the projectiles, like here, to make sure it looks okay before writing to file. Also, I just found out that this axis 1 list with a background picture doesn't need to be returned here, which can speed up the animation quite a bit, at least when showing it live. I think this axis 1 is only needed here if one needs to do certain operations on the background picture, such as changing the transparency. But for normal cases, it just needs to be imshow to this ax_b, but it doesn't have to be returned on here, which makes sense since it isn't animated. One file that I really like to keep in this folder here is called trig functions. It's a module just used for plotting. If one is programming animations or anything data science related, it's inevitable that one will use various functions to generate data, events, or the like. So it's really nice to have this module with mathematical functions that can be important by the animation program, but which can also be called from down here in its own main function, for example, to see what kind of in-out one gets using some function to set the alpha or size of objects, for example. This can also be done online using tools such as the Desmos graphing calculator. I usually also have a dedicated tutorials folder. Say when one finds some code on Stack Overflow or generated by some AI like ChatGPT that one wants to test, just drop it in here and run it. This is just part of fundamental Git. In this video, I'm just going to talk about the git ignore. You really want to make sure that all big files are ignored. In this case, it's only the video files. So basically what you're looking at right now, they're about 200 megabytes. And so they don't appear in the GitHub repo. Git ignore is not just about learning how to avoid exceeding the free quota. It's also that it's really important to make sure this .git folder is not growing too large, because once it does, the only simple way to fix it is to migrate the repo to a new one. Another Git thing is that a commit, at least in an animation project, can represent an actual rendered video. The way I do it is to run the animation program to save a video and then commit with the name of the video. So then one can go back and have a look at the video and the corresponding code that delivered the video. If you haven't gotten around to using version control yet, it's never too late, and it's really good given how much return one gets from a few hours of learning. Learning Git well takes a lot of time, but once one gets through the basics, it starts feeling natural and also empowering. For debugging, it's good to know about random seeds. It's crucial to be able to reproduce whatever bugs that are generated due to a random number. And there's only one lesson. You don't set random seeds in different places. You set them in main.py, and if that doesn't work for whatever reason, then set them in a different single place and keep them there and change them there. A code project with good documentation shows that the dev likes to explain things, has patience, etc. I'm not going to pretend that this project is well documented. A rule of thumb is that 50% of everything in the project should be documentation, mostly in the form of comments, and it's nowhere close to that. With the lame excuse that all this code is written and used by just one person. Ideally, this type of function comment should include descriptions of these parameters, and README should of course not be empty. But one thing that I tend to not forget to write comments about is bugs. I try to never delete comments that have to do with bugs that were encountered and how they were fixed. Some people say comments just populate the editor with noise, but the simple remedy to that is to get comfortable with collapsing them. So this comment, for example, describes a bug that was fixed a long time ago, but I just keep it collapsed and hover the mouse over it if I want to read about it. In the moment, writing about the bug may feel like, oh, what the hell, this is insignificant, but I often surprise myself reading them at a later stage. There are times when one will find oneself reading them. Here there was a big bug a long time ago, and I actually deleted it apart from keeping this one line. So it's like a big roadside warning sign. An accident has happened here, and it may happen again if one isn't careful. This is like a second part of the video, which talks a little about the functions used to animate projectiles, clouds, and waves. For the projectiles and waves, the code is in these helper modules, and the movement of the clouds is just a NumPy linspace, so it doesn't get its own module. Previously I made a video about how one can animate a moving cloud in the form of a PNG picture, link in the description. It looked at 3 ways to do it: set extent, affine 2D using the Matplotlib transforms library, and warp affine using CV2. Among other things, the previous video concluded that Matplotlib affine 2D is easier and faster than CV2 warp affine, but that it doesn't look as good, and I think it has to do with the boring fact that there is no free lunch. If an animation looks great, it probably means that it took a long time to render. Set extent is not really a viable option, since it is outmatched by Matplotlib affine 2D in terms of CPU time and capability. There are some tricks one can use for some animations to use Matplotlib affine 2D instead of warp affine. This cloud here, for example, is animated using Matplotlib affine 2D, and it's made up of several smaller clouds that have a low transparency. Each of them looks pretty bad, like the same bad as in the previous video when viewed as a singleton with no transparency. When many with high transparency are used, it looks much better. Another thing is that FPS was increased from 20 to 80 here, and it seems to help to some extent. One thing one can also try is to increase the resolution, but it has a huge impact on rendering time, and I haven't managed to conclude how much it actually helps to fix affine 2D. Like, it's still a jumpy motion. The resolution and FPS seem to not matter as much as the speed with which the object moves. And so if one needs to animate an object that moves really slowly, the only thing that I found seems to work okay is to cut the object into pieces and use transparency. This method is just a hack, I would say, and it would be awesome if the Matplotlib code would be updated to produce more smooth motion like CV2 Warp Affine, while still being really fast. Or even better if there's a mistake in this code, but I don't see what it could be. These XY values are continuous NumPy lin spaces. Also, a mistake in the old video, calling Affine to D is not hundreds of times faster than calling Warp Affine in CV2, like I said there, at least when writing it to file. And in that case, it's more like 10% faster. And that's because the FFmpeg writer is the bottleneck when writing to file. The big advantage of Affine 2D is rather that it's easier to work with. One doesn't need triangles and one doesn't need to write code that figures out the extent of the warp in CV2. And these chain transformations are pretty intuitive. I'm not going to talk about the projectile motion because that is also something covered before, apart from mentioning that there's a worse and better time in flight equation. Here's what the worst one looks like. That tends to be easier to find online. The bad thing with it is that it assumes that the projectile is launched from ground level, and it doesn't work for fireworks because they explode up in the air and then fall some height before hitting the ground. So here's the better equation, and it has this height variable, so it generalizes the case. If one wants to start from the ground, one can still do it just by setting the height to 0. For the waves, they're so-called Gerstner or trochoidal waves. They're described pretty good on Wikipedia, so reproducing this animation on the right is a good way to start. But it has a bit of a steep learning curve to implement it straight away with these equations, and there are some more pedagogic materials online, like this PDF that I found, which provides code samples in Unity, but that doesn't matter. The equations are the same, and the nice thing with this one is that it starts with simple sinus waves and then progressively builds up towards the Gerstner waves. This animation uses 2 Gerstner waves, and they are generated using this XY array for each point. So each point moves in a circle, and this STN is the steepness of the wave. K is the number of waves that are shown on the extent of the surface, and D is the XY direction of a wave. And they're both in the range 0 to 1. A and Z provide the starting position on a Cartesian plane, and C is the wave's speed. Doing it like this in for loops for each waypoint is crazy, and it could of course be optimized, but for serious water animation one shouldn't even use Python anyway. It's just never gonna scale. But it's definitely possible for smaller things and fun to work hands-on with these parameters, and that is also a point. You don't have to do this in some fancy 3D animation program. There's plenty of fun to be had and things that one can learn about waves that are available if one just knows some basic Python and Matplotlib. The alpha or transparency is also done here, and the point there was to try and make the crests of the waves stand out more. There one can also play around with the XY coordinates of the points and their tangents. These first 2 are XY tangents, and the third one is the gradient.